let me just say one more thing about this. This spectral sequence. So even when p is 2, and the homology of this complex in degree 1 is the Durham-Witt. For C, or yeah. Yeah. So remember, this here is the homology, cohomology in degree 1 of a complex that lives here, and so the differential in that complex is something that we have not had before, and that's so the differential in W of 1, this should give rise to explicit, what is it there called, residue? What are these things called? Laws, reciprocity, explicit reciprocity laws, is that what it's called? What is it it's called? It's when you calculate the map from Milnor K-theory to Ital cohomology. What? No. I forget what it's called. So Cato has done this using symptomic cohomology when p is greater, when p is odd, but for p equal to 2 is still missing. And but now it should be possible to do that by using this complex. So okay, so now let's fix a prime p and let WA be the category of p-typical Witt complexes over A. So given a ring homomorphism from A to B, there's inverse image, direct image functors, or adjunction between Witt vectors over A and Witt vectors Witt complexes over A and Witt complexes over B. Like this. So yeah. Now since so the inverse image functor will preserve co-limits, in particular it will preserve initial object. So the inverse image of W omega A is W omega B. So okay, so now I will give a formula for this inverse image functor when f is the map from A to a polynomial algebra over A given by that map. So and a C-localized P algebra. Yeah, so if we have a Witt complex over, let's see, if we have a Witt complex over B, is that right? Then we have no, a Witt complex over A, then we have a unit of this adjunction like this. Here.
So if we have lower star, a restriction factor in the sense
Yeah.
it keeps the underlying leading
Yeah.
and the underlying differential.
Yeah, so it's just, yeah. And, yeah, okay. Yeah, and then so the only thing is that you have this map. No. Here, and now you compose that. Well, I guess here. Now you compose that with that map. Yeah. Okay. So now consider the maps of abelian groups from here to and as Stefan just said, this is the same as this is the same abelian group as this abelian group that to omega assigns the basic Witt differential of the following types. So there's 4 types here. So if so for s equal to 0 and j natural number which includes 0 and epsilon equal to 0, e of s j epsilon of omega is eta of omega times the Teichmüller of x to the j. So I don't write the lambda here. And for also for s equal to 0 and j not 0 and epsilon equal to 1, e of s j epsilon omega is eta of omega times x n to the j minus 1 dx. And 3. So for S greater than or equal to 1 less than n, j not divisible by p, and epsilon equal to 0, E is j epsilon of omega is v to the s of eta omega times x n minus s to the j. And finally, for the same s and j and epsilon equal to 1, E of s j omega is dv to the s. So it's just d of this. Like this. So as s, j, and epsilon vary, as in these formulas, the basic width differentials define a map of abelian groups from this group defined to be the sum of all of the domains of these basic width differentials. So here E I minus epsilon n minus s. So this is sum over s, j, and epsilon, and then from here to if upper star E I n. And hold on. Yeah. So, and now there's the following theorem. So by myself and Ib Madsen, when p is odd, and Costiano when p is 2, which says that there's a unique structure of p-typical width complex on over ax, such that this map is a natural transformation of functors from p-typical width complexes over A to p-typical width complexes over the polynomial algebra. And moreover, this map is an isomorphism. Yeah, this is a lot of work to prove this theorem. So what is the statement? The statement is that if you take, let's take any two of these basic width differentials and then multiply them with each other, for example, then there's a unique way to express this as a sum of such width differentials that will make this a map of width complexes. And so when you think through all those possibilities, you can then write down what the product on this thing must be. Then you have to show that that is associative. And that's quite a lot of work. Then the same thing with the F. So there's a unique way to define an F here on these basic width differentials so that this becomes a map of width complexes. And then you have to show that it satisfies what it has, what it should. And so that's quite a lot of work. In the case of the Rham-Witt complex, you can cheat by using this theorem I proved or I stated at the end of the last hour, namely that the map from Rham-Witt to CR is an isomorphism for C is an isomorphism for I less than or equal to 2. So as I will now explain, the formula holds on this side and by topology, and therefore proving that the relations hold, we can read off over here. Yeah. So now let me call this a proposition because it's much easier that if A is a C localized at P algebra, then this map here, so this is this map is an isomorphism. So yeah, so how do you prove such a thing? Well, Th of a monoid algebra such as this is canonically equivalent to Th of the ring of coefficients, since the cyclic bar construction on the monoid. So this is the cyclic bar construction on a free monoid with one generator X. And now that decomposes as a direct sum now at disjoint union over J greater than or equal to 0 of pieces like this. And here. So, so here, let me say, so the homology of this piece, here if J is positive, is an exterior, well, so it's, so let's see, H naught is C generated by X to the J, and H1, let's change them. Is C generated by this, and Connes operator here is Connes operator, is the formal differential. So it multiplies by J here. So let's see, what is it we would like to understand? We would like to understand THH of A, and then these pieces, and then fixed sets of that, like this. So this is an equivariant homology theory corresponding to this equivariant spectrum of this guy. And this, so there we have, as Wolfgang mentioned earlier this week, we have the equivariant at here. Here's a Brooke spectral sequence. Beginning with the Bredon cohomology of this space with coefficients in this, the Mackey functor that are the homotopy groups of this. Oops, here, and then converging to this group. And now I'm doing it, now this is the group. So, G. And now this is a summand or maybe we could also have, if we didn't do these summands, then this would exactly be the group. So, but let's say that this is the jth summand in CR in S plus T of the polynomial algebra. So, so this equivariant at here's Brooke spectral sequence is very often very complicated. So, for example, even for equivariant K-theory, topological equivariant K-theory for the cyclic group of order 2, there are infinitely many differentials in this spectral sequence, and it's very complicated. So, but here this is just a circle. So this is a case where you can actually understand this quite easily, and then you get precisely this result out of it. Okay. Yeah. So, as a corollary of this, we get that the canonical map from Wn omega A star tensor Trn star of Fp to Trn star of A is an isomorphism for a polynomial algebra over Fp. So why is that? So proof, it's true trivially for n equal to 0. So if it's just Fp, the Rham complex of Fp is concentrated in degree 0. This is true for every perfect ring. Why is that? Because if you're perfect, then any x can be written as y to the p, and therefore dx is p y to the p minus 1 dy. And if you're in characteristic p, this is trivial. This is 0, so there are no differentials if you're perfect. So it's true when n is 0, and now if we apply this construction p on both sides, yeah. So let me say in induction step, so let's say that we have already proved this for some n. Well, if we have an isomorphism and we apply a functor to it, it's still an isomorphism, which is one of the good things about a functor. And and now, on the one hand, this is that, and this is oops. Is that, and this diagram commutes because this is a natural transformation, and so now we get the induction. Okay, so this was so for polynomial algebras over Fp. This is an isomorphism. So when when I had just graduated and I was a postdoc at the Mittag-Leffler Institute, I had proved this result, and then I told it to Bob Thomason, who came to visit. And then he said, then it must be true for any smooth algebra. And then I asked, what is a smooth algebra? And, and then he took me to the library and showed me EGA4, which is a fantastic source with all the details. And yeah, so to extend to smooth algebras, we need to know how these constructions behave with respect to étale maps. Let me state a general theorem which was proved recently, or 5 years ago, approximately by Jim Borger. It turned out that it had been proved before without anybody in arithmetic geometry noticing by van der Kallen. Or van der Kallen said that he needed this result, and then Garber told him the proof. So, yeah. So if F is an étale map of rings, then so is the induced map on Witt vectors.
Is this typical or
The only thing that it's true for both, but it's important that it's finite. So it has to be a finite truncation set. Moreover, if we go from here to here by F, well, let me write it as above. Yeah, so if we go here by this étale morphism, and then go here by the Witt vector Frobenius, then this diagram is co-Cartesian. So in other words, the unique map from the tensor product of this and this over that to here is an isomorphism. The same thing is true with the restriction maps, but that's actually a consequence of this. So okay. Okay, so now first, if this is étale, then then the induced map, then this map here is what is this map? This induces a map on Durham-Witt complexes, and now this is a Wn of b module, so we can extend scalars up like this, and that extended map is then an isomorphism. How do you prove this? You prove it by making an inverse. And so what do we have to do to make an inverse? Well, if we can prove that this side is Witt complex over B, then we get an inverse map, and then we have to show that it is the inverse. So show that the left-hand side is a p-typical Witt complex over B. So now I should speak correctly. Has the structure of a p-typical. Okay, so to do that we have to define these various maps. So first the differential. So let's see, so Wn of B here we have a differential to Wn to omega 1. And since this map of Witt rings is étal, this is isomorphic to this. And now we have a canonical projection from omega 1 Wn to Wn omega 1. So okay, and so using this this composite, we get the differential here in when I is 0, and from that you get it for higher I. 2. Why? Oh, maybe. I don't think this is true for formulae étal. But
I was just thinking about the construction you indicated earlier, the construction with the Rham complex of the program complex.
Yeah. Okay. F is F tensor F, R is R tensor R, and now to define the Verschiebung, we use that this square is Cartesian. So that tells us that this here by F tensor the identity is the same as that, and now we use V in that here. Okay, so now we have defined all the maps. We still have to prove that the relations hold, and I actually think that there's well. So the tricky one is the last one, that if the Theis-Müller A is Theis-Müller A to the p minus 1 d Theis-Müller A. So how do you prove that? Let's see. So we have omega 1 WNB. So by Borger-Wieland, we already have this divided Frobenius on Kähler differentials. And now, again, by the etalness, this is Wn of B, tensor over Wn A, omega Wn A1. And this is the same thing. And this is F tensor F. And now here we have the projection. Here. And so the formulae we want to, well, first of all, by the definition of the F, the divided Frobenius in the de Rham complex, it's defined so that this square here commutes. So this commutes by definition. And now the formula that we want to prove holds in here by Borger-Wieland. So the way that it comes out of lambda operations or lambda rings, it's a formal consequence that that formula holds here. And so that proves the theorem. I actually believe that that there was a gap at this point in earlier arguments. Yeah. So now the same theorem holds for TR. And another way of stating this theorem and the corresponding theorem for TR is to say that TR and the de Rham-Witt complex are quasi-coherent sheaves of WNOX modules on the small étale side of X. Yeah, so let me also just state that theorem. So then yeah, and so now with these, from these and from the structure of smooth algebras, it follows that this is true for any smooth FP algebra. And then there's this fantastic theorem of Popescu that every regular FP algebra is a filtered co-limit of smooth FP algebras. So in fact, this is true for a regular FP algebra. So I think this is a good place to stop.
Thanks a lot for this nice talk. Previous ones. Do we have some questions? No.
Yeah, So remember this basic theorem which I stated on Tuesday, that for Fp, this Frobenius is an equivalence in non-negative degrees. So this here, the homotopy groups here, was a polynomial algebra on the divided Bott elements, and this is then obtained from that by inverting that. So this becomes a Laurent polynomial algebra. Yeah. So this then implies that Tf of Fp to Tp that the same thing is true here, that this is an equivalence in non-negative degrees. And now from these descriptions here, it then follows that if A is, let's say, smooth over Fp, then this is an equivalence in degrees greater than or equal to the dimension. So for like that. Yeah, and this part here, this gives a calculation of what that is in terms of the drum bit.
Thank Lars very much again for coming to Bonn. Whole series of lectures. I hope to see you back again soon.